everyone, so I'm Langlet Nathan, a second year PhD student at Onera in Paris, and today I will present you my work on automatized flow distortion and swirl generation using topology optimization. So I will start this talk by giving you the context and the objective of the study. Then I will explain you how to formulate a topology optimization problem with two examples. Then I will discuss the future work of the thesis. So, in many internal flow engineering applications, designers aim to achieve a specific velocity distribution. For example, in Airbusing aerospace propulsion systems, the velocity distribution at the AIP is critical for the engine performance and reliability. So, as you can see here, a classic example is the flow inside an S-shaped duct. This configuration induces a low stagnation pressure region at the AIP due to the flow separation. So, for that, manufacturers aim at accurately replicating the flow distortion and swirl on dedicated ground test rigs with various strategies. So they can use a porous grid to generate a stagnation pressure pattern, but they can also introduce obstacles in the flow, like strip, in order to generate a target Mach number distribution. Their shape and position are adjusted by a trial and error process, which is time-consuming and very costly. A second example is the duct with an 80-degree bend, which are often necessary in many industrial applications, like aerodynamic wind tunnel, air conditioning, and it uses a massive flow separation that influences the system efficiency. For that, guide vanes are employed to restore a uniform flow without the turbulence or secondary flow. But like the previous example, they are designed with very tedious methods. That's why a fully automated approach to design the distortion swirl generator or guide vane will be highly beneficial. Topology optimization is a very promising approach, and we will use this method to identify the areas where the solid material should be introduced in a design zone in order to minimize a cost function representing the quadratic error to reproduce a target velocity field in an evaluation zone. No such topology optimization exists in the literature, and especially at very high Reynolds number. That's why we will use this study as a first step, and we will use topology optimization to define geometry able to reproduce a given target velocity profile. Okay, so now let's formulate the topology optimization problem. The most commonly used methods are based on a pseudo-density field, alpha, to model the fluid or the solid. And there are two approaches to represent the fluid and the solid. So there are the continuous approach, where alpha is continuous between 0 and 1, and the discrete approach, where alpha is equal to 0 or 1. So in this study, 0 will be to solid and 1 to fluid. And in this study, I will focus on this discrete approach. Using the Dorsey-Brinkman penalization term in the Navier-Stokes momentum equation permits to model the fluid or the solid. Its value is given as the net interpolation between two extreme values, kappa min and kappa max, the value of alpha, so if we are in a solid or fluid, and a relaxation parameter Q. So, in the fluid, we want to recover the classical momentum equation. So we set kappa min equal to 0. But in the solid, to ensure the 0 velocity, kappa max must be high enough. So in this study, I will consider the Wentz equation for an incompressible steady flow with the Spalart-Allmaras turbulence model. And the distance to the wall is obtained by solving a modified eikonal equation. And as you can see, each equation has a penalization term to take into account the solid. So like I said in the introduction, the objective function is defined as a quadratic error between the actual velocity and the target one at the evaluation zone. And now we can formulate the topology optimization problem such that minimize the objective function, such that the residual of the governing equation are equal to 0, with a fluid volume constraint in the design zone and a pseudo-density constraint alpha between 0 and 1. But now we can consider a first-order Taylor approximation to linearize this problem and to obtain the TOBS method, where alpha is a binary variable, 0 or 1. This problem is solved by an integral linear programming optimizer, CPLEX in our case. And you can see a new constraint which limits the number of change between the solid and the solid and the fluid at each CPLEX optimization iteration. So, not a surprise, but the topology optimization loop is implemented in FEniCSx in order to solve the nonlinear problem, but also to compute the gradient of the objective function by solving the adjoint problem. The pseudodensity field alpha is updated by CPLEX until the convergence, and after the optimization, we extract the solid from the funnel field with pointwise, and we create a body-fitted mesh to compare with the optimization. So let's move on the first application, 2D flow in a 90-degree band. So like I said in the introduction, this configuration induces a massive flow separation after the band. So the objective of this test case is to automatically design aerodynamic structure in the design zone in order to suppress the flow separation and restore a uniform velocity profile in the evaluation zone. So for that, we consider a flow at a Reynolds number of 10,000. We allow 3% of flip limit between fluid and solid at each iteration, and 80% of fluid are allowing in the design zone. So now I will show you an animation of the optimization process. So as you can see, the optimizer introduces a solid in the inner and outer region of the band in order to suppress the flow separation. But even if the objective function decreases significantly during the optimization, the velocity profile does not always meet the 5% target criteria. So I have created 3 other cases with different initial states in order to explore the design space of this complex case. So the case 2 and 3 introduce small plates, and the last one introduce a square at the center of the band. So I will show you the third case, and as you can see, the optimizer directly modified the small plates in order to recreate the guide vanes. So as you can see here, our approach consistently leads to a design with guide vane, redirecting the flow, and we have a uniform velocity profile in the evaluation zone. So as you can see on the evolution of the velocity profile in the evaluation zone, the case 2, 3, and 4 yields more efficient design than the first case. And the last case needs more iteration to converge because the method is less efficient to reduce the solid than to create the solid. So let's now talk about the 3G application. So like I said in the introduction, military air intakes are often associated with vortices. So the goal of this case is to reproduce a pair of counter-rotating vortices in a duct. So for that, we consider a flow in a duct at a Reynolds number of 1,000. So we don't consider the Spalart-Allmaras turbulence model, and we allow 90% of fluid in the design zone. So we can see the evolution of the objective function, the volume fraction, and the design at 3 different iterations. As you can see that rapidly the optimization introduces thin plates facing the flow. And at around 40 iterations, the objective function has decreased significantly. And the obstacle features an inclination angle of 45 degrees, so like the vortex generator. And then the optimizer reduces the quantity of solid in order to converge and to be equal to the volume fraction. And at the end, we obtain of pair of counter-rotating vortices. So now I challenge you to find where is the optimization velocity profile and the optimization one. Not easy. So as a conclusion, the future work are we will focus on adapting the method for high Reynolds number 3D compressible flow. So I'm working on a compressible once stabilized by SUPG solver in FEniCSx, solved by FGMRIS. So I have already pretty good results in 2D and 3D. So thank you for your attention.
Okay. So let's open the floor for questions. Paul.
In your objective function, you have an error to prescribe velocity field. How do you construct that?
What?
In your objective function, you have the squared error of the prescribed velocity field, your target velocity field. How do you come up with that? How do you know a priori where you want to end up with the optimized design?
I don't understand the question, sorry. Can you repeat slowly, please?
Okay, yes. In your objective, you have the error of your velocity field, of the optimization, and
Yes.
the target field, right? So sorry. Yes, do you hear me? So in the objective, you have the error between the velocity field and the prescribed one, the VD, right? The V you optimize for. But how do you figure out what is your desired optimized design that you're driving for?
I don't understand the end of the question.
Yes.
Oh, okay. In the first case, the target velocity profile is obtained in the literature from a study at this exact Reynolds number. And for the last case, I was a little fast, but I created my own target velocity profile with this vortex generator, and this velocity profile. So you can see this the velocity is the target velocity profile I use in the optimization. Does it?
I have a follow-up question maybe to that. So then you're basically losing a target profile that already is from a predefined design. Why should that be the good one, right? Why does it make your objective driving for a better design than in the first place?
I have a lot, there is a lot of obstacles possible to obtain the right, the target velocity profile. So here I only show you the efficient design, but yes, if I change the length of the design zone, if I change the constraint in volume, I always obtain a new design. So yes, it's a lot of simulation, but in general, all the simulation leads to a good and efficient design, which is very good for the thesis.
Okay, thank you.
Yes.
Yes, one here.
About computational resources, so did you use a cluster for months or?
For all the simulation, I'm using a Sator cluster of Onera. So I think, so you can see here, for example, the number of processors used. And in 3D, and now in 3D dimension, with turbulent flow, I need a lot more of processors. So.
And there was another question here.
What happens when the optimization procedure leads to a structure that is hard to fabricate? For example, I think that
That's a very good question, because the goal of the thesis is to use this method to generate automatically the distortion. So for the moment, we only test the method, and we discover the method for this type of application. So we don't have, for the moment, the solid has always been one solid in the fluid. Never small island or something like that. But for the moment, as you can see, the solid is in the middle of the duct. So I found a paper in the literature which permit to have solid attached to the wall, for example. So we will see that in the third year.
Okay, let's thank the speaker again, and that draws the session to a close.